All right. Hello, everyone. So this talk is about dynamically check deep immutability in Python, and it's work with me and the lovely people you can see up there. So immutability has been well studied by our community, right? It gives us the ability to reason about programs better, it allows optimizations, and it allows us to share stuff in concurrent setting without needing synchronization. As such, it's also employed in many languages. Common ones are functional programming languages. Here I have, for example, Erlang or Clojure. And here immutability is deep. Deep meaning that if we have one object that is immutable, all objects reachable from this object also have to be immutable. And in functional programming languages, this is often enforced by simply having no mutation operations. So if you have no operations that can mutate stuff, ergo you don't need to enforce it. Then we have languages like Rust, which we've just heard about, and Pony. And here you also have deep immutability. But this deep immutability is enforced by an ownership model. Then we have imperative languages, take Java and C++, where we have shallow immutability. And shallow immutability meaning that we can have an immutable object that actually points to mutable ones. And here it's often enforced with a type system and the support of keywords like final and const. And then we have Python, right? This is what this talk is about. And Python kind of doesn't have a concept of immutability. There are some objects which have some enforcement, but there is no global concept, and therefore also no real enforcement. And this brings us to what we've done. So we have designed deep immutability for Python with a specific goal of sharing data across threads. And with this, we've achieved a beautiful graph over there, and I'm going to tell you the journey how we got there. But to highlight is that the blue graph is what's possible on current stable Python, and the orange one is what we've achieved. And we've also found generalizable concepts. So if you, in your language, want to add dynamically check deep immutability, these will be super interesting to you. This is, for one, feasibility. This is a way to control if and how objects can become immutable. And detachment, a way to control and prevent immutability from propagating too far. Now, some of you looking at the graph may wonder, isn't Python non-concurrent? Isn't that what a lot of discussions are currently about? And it turns out that Python currently has a global interpreter lock. So whenever the interpreter tries to execute some bytecode, it has to acquire this lock. But there is a push from the community to change this, or at least make Python more concurrent. One of the best known ones is free-threaded Python. This is currently experimental, and this one is basically, what if we remove the GIL? But there's also a proposal of sub-interpreters. And this proposal is actually stable since Python 3.12. And sub-interpreters allow you to run multiple interpreters in one process, but critically, nothing is shared. This is isolated interpreters. Let's look at this in a little bit more detail. For this, we have our single Python process here. This is your proper, usual, single-threaded Python. And this beautiful process can create mutable objects like every other day. But with the addition, or with sub-interpreters, it is possible to spawn a second sub-interpreter with a second thread running. And the important part is they are completely isolated. It is not possible for interpreter 2 to see the objects of interpreter 1. This is cool on the concurrency perspective because you don't need synchronization, but it makes communication hard, right? So in stable Python, what you have to do is you have to manually copy all data over, which is not necessarily efficient. So this is where immutability comes in. If we can turn these objects immutable, annotated as this ice blue in this presentation, then we can, in theory, share these objects across two sub-interpreters without needing synchronization between the two of them, right? Because the objects are immutable. There's nothing to synchronize about. So our goal with this work was to enable sharing across sub-interpreters. And we also wanted this to be sound. We needed this as a language-level construct to allow us reasoning about it, and for the runtime to support this, for example, also the direct sharing. But we are not designing this in a vacuum, right? We have certain restrictions, and the first one is Python doesn't have a type system. So we can't rely on existing immutability designs and have to do something that works for Python. And then there's also the problem that Python has a gigantic ecosystem. This means that our design has to be A, backwards compatible, and it should be opt-in, so that existing programs can continue work. Let's start with a basic idea of how you may implement this in your language. So let's, for every object we have, add a small flag. And this flag basically just says, hey, is an object mutable? This is what every object in Python is by default. Or if the flag is set, it's immutable. Then we add an operation called freeze. And this operation basically just marks all objects and objects reachable from this object as immutable. So if we look at our two variables over there and we freeze x, then we can see how mutability propagates through the graph. This is beautiful. And lastly, there are some checks in the runtime that whenever you try to modify an object, throw an exception. So if we would try to assign something, the runtime would say, hey, you try to modify an immutable object, not cool. So with this basic idea and understanding in place, let's look at an actual Python program. So here we have a beautiful small script that, and I'm going to walk through it step by step. So the first import statement here creates a Python object that is mutable that represents this module. This import module does the same thing, but here critically we've also shown the pointer to the function object, which is a stateful mutable object in Python. Because of course. So then we continue to this class, and this one creates another mutable stateful object that we somehow have to deal with in our design. And each method is also reified. We here don't visualize the init function, but there is this roll function which also has a pointer to the globals, and this is how you can access, for example, the random module. And now when we instantiate two things, for example, our D6 here, which is a beautiful die, this has a pointer to its type, and the same goes for our D12. Now, if we try to freeze our D6 here, interesting things happen. And this is that freezing propagates via the type and via functions through the entire system. So in this example, where we want to preserve our beautiful D6, all of a sudden, our D12 is frozen, and even worse, the entire interpreter crashed. Why is this? Well, it turns out that Python, at least the REPL, requires the sys module to be mutable because whenever you execute something in the REPL, it assigns to the underscore value in the sys module. This is not great. So this brings us to one of the generalizable concepts, and that is freezability. Basically, we needed a way to control if and how objects can become immutable. If we look at this program and roll it back a step, we can mark the sys module as unfreezable. So this sets a flag saying this cannot be turned immutable. And we can also go to the runtime and request this, and the runtime will say, don't freeze this. And any attempts to do this will result in an exception and the interpreter preventing you from doing that. All right. So the solution for the problem that the sys module has to be mutable is to make it unfreezable. Great. But this again brings us back to our core problem of every object is interconnected in Python. And this is where detachment comes into play. This is a way to control how far deep immutability propagates. So again, if we have our beautiful program here, and we wanted to free as our D6, we can do the freeze call, and it propagates to this type. But at the point where we encounter a function object, this immutable stateful object, we pause for, or we don't pause for a second. As part of the freeze, there is logic that detaches the function from the global scope, so this prevents it from propagating through the entire system. And we do a small static analysis that finds all global variables that we actually need. And this way, we've detached the function from the global scope. And now, once we've done this as part of freezing, freezing continues to propagate, and we have a frozen D6 object. This is perfect. So the solution for this interconnected web that we have to deal with is detachment. Though this story is not done yet. If you try to run the roll function, you get an exception. And the reality is that a lot of Python modules are stateful. The solution here is, again, detachment. I sadly don't have time to show you any details of this way, but I encourage you to read the paper where we discuss 5 different ways of detachment. Let's talk a little bit about the implementation. We've authored our implementation on an alpha version of Python 3.15, which was the most up-to-date version when we submitted the paper. Our changes are 7,000 lines of logic to do freeze propagation, detachment, and plus escape hatches. 7,000 lines in a context of a code base that's 2.7 million lines of code is good. And we provide this, of course, as a workable and reusable artifact. As part of our implementation, we've also support atomic reference counting for immutable objects. So this is why we, for example, needed to implement that in the core of the runtime. And there's a question, how do we enforce this? And the simple answer is we use a write barrier. Let's visualize it for a second. Let's say we have this function, this beautiful function that increments a counter. The current version may look something like this, but to support immutability, you have to add a small check. And this PyCheckWrite basically just says, hey, if this object is mutable, you may proceed. Otherwise, we have to emit an error and propagate this error upwards. In total, we needed to insert this write barrier at 148 places in the runtime. But with this, we covered the entire interpreter, all standard libraries, and so on. Evaluation. We have, to evaluate backwards compatibility, we've ran the entire CPython test suite. For reference, this is about 600,000 lines of Python code that works. And we believe that this shows that our design is opt-in and backwards compatible. Of course, there's also a question about correctness. And for this, we've added our own tests, about 3.6 thousand lines of code, testing various bits. And whenever we found something, we added it. Let's talk about performance, which may be super interesting, and some people have been waiting for this. And for this, we've used the PyPerformance benchmark suite. This is a typical benchmarking suite used in Python. And this is the graph produced by it. Of the significant results, we got a slowdown of 3.6%. In the graph, I will mark it right there. And this is of single-threaded programs, so none of these use immutability. We consider these results very good, given that we haven't spent time on optimizing it yet. We've added write barriers on hot path of the runtime, and other proposals like free-threaded Python target a slowdown of 10 to 15% of single-threaded programs. So having a slowdown of just 3.6% geomean is quite good. But let's talk about the thing why we've actually been doing this, right? And this is to share objects across subinterpreters. First, we've benchmarked how long it takes to freeze an object opposed to copying it once, right? And as you can see, freezing is in all cases faster. In some cases, that includes custom classes like the student as actually significant, like larger by a big portion. And this is also visible if we distribute work across subinterpreters. So in this benchmark, we've scheduled 4x4 matrix inversions across several subinterpreters. And the blue graph at the bottom shows what is currently possible on stable Python. So this is for every cent, you have to create a copy of it. While freeze is done once. So we freeze a matrix once, and afterwards we can freely send it to every subinterpreter to do the matrix inversion. And that is one of the big reasons why we see such a performance increase. Yes, in the paper you will find a lot more details about this and external things. So there is a discussion about design goals and how we fulfill them, an explanation of how freeze propagation works. As part of this, we also needed to handle freeze failure. So how do we undo this and surface it to the user? We also needed to implement a way to collect immutable garbage without tracing. As I mentioned, there are 5 different types of detachment which we've documented, plus escape hatches that the community has asked for. And there's also pre-freeze hook, among other things. This slide is limited, like the slide space. What are the next steps? Well, we've already created a Python enhanced proposal to engage with the community, see if we can get this into language and get that accepted. Next month, we will speak at EuroPython, actually present our design and the benefits of this design. And as part of it, we will also talk to the core Python community, the developers of the runtime, to see how we can potentially shape the future of Python and enable safe concurrency in this language. Thank you very much.
Questions?
Hi, thanks for the great talk. So the mechanism you've introduced is really elegant, and it's like, you know, backwards compatible because users have to opt into it. But have you thought about how you can encourage users to add these freeze calls? Because it's no use if nobody wants to use it. Obviously, they're motivated by performance, but I'm just wondering if there's any way to surface that to like users to adopt this.
So a thing I haven't talked about, which may slightly already answer that question, is that some objects, as I mentioned, are already immutable in Python. So we provide a way to say this object is already logically immutable. You can actually, it turns immutable if you observe this. So integers, for example, or strings can already be shared without you needing an explicit freeze. And we see this as a like opt-in mechanism specifically when people want to share or want this ability to reason about it. So yeah, encouragement is based on what the users need and want, right?
Cool, thank you.
You're welcome.
Time for another question? Oh.
Hi, thanks again for the talk. Can you talk a little bit more about how the detachment works? Especially, is detachment more of like a device that we put in, or that has any sort of operational aspect to it? Like, does that involve deep copying of all the reachable objects into the system library?
So when we started working on this, we found that we needed to detach one or two things, and it just became more until we like reached 5. And we figured out that there's actually a core mechanic of when before you freeze an object, would it be a custom type, you want to call a little bit of code. So you can, for your own type, define how it works. In most cases here, we've repoint pointers and, like we've shown there, replace the global dictionary with a new dictionary and only copy over the references of the needed objects. But you could fully imagine a world where you do deep copies of everything. And you could define them for your own type if you wanted to.
I see. So just to clarify, these are objects that are inherently immutable, but through the awfulness of Python interpreters that they ended up being part of the mutable object.
They are inherently mutable. You can, every function, like function objects, you can just add new globals to it, new locals. There is not really a restriction. It's just that most Python programmers don't do that because it makes it really hard to understand what's going on. But functions are just stateful, mutable objects. There's nothing stopping you.
Got it. Thank you.
Is there one other question?
Hi, very cool talk. One curiosity question just about something you mentioned briefly is that for every object you added a very small flag indicating whether it was mutable or not. Have you done any profiling of how that affects memory usage?
So luckily, Python objects already have few bits that are not used in the header, and they specifically have a flags field. So we've added it just to this one, and the object header actually did not increase. But that is a very good question. Thank you for asking it.
Thanks again.